Inside the cockpit of the Sukhoi Su-25, the pilot is encased in a continuously welded half-inch thick box of ABVT20 titanium alloy. This 10 to 24 millimeter thick metal tub weighs over 1,000 pounds empty. It is not bolted onto the airframe as an afterthought. It is the core structural component around which the forward fuselage is built. In military aviation, engineers spend entire careers agonizing over ounces, shaving grams off bulkheads to maximize payload and range. Yet Soviet designers intentionally anchored a half-ton metallic bank vault into the nose of a relatively small twin-engine attack jet. They did this because they accepted a brutal operational reality that Western designers spent decades trying to engineer their way out of. The Western philosophy of close air support eventually evolved towards standoff precision, utilizing advanced sensors and guided munitions to hit ground targets from altitudes where anti-aircraft artillery could not reach them. The Soviet doctrine, forged in the mechanized philosophies of the Cold War and refined in the brutal mountain valleys of Afghanistan, made a completely different assumption. They assumed their close air support aircraft were going straight into the mud. They assumed the aircraft would be tracked, targeted, and repeatedly struck by heavy machine guns, automatic cannons, and shoulder-fired missiles. The Su-25, known by its NATO reporting name Frogfoot and affectionately called the Grak or Rook by its crews, was built for a tactical environment defined by massive, unavoidable attrition. It was designed to fly low, absorb catastrophic kinetic impacts, deliver a localized barrage of unguided firepower, and limp back to a dirt runway missing half its control surfaces. To understand the Su-25 is to understand a doctrine that views the aircraft not as a delicate, high-altitude surgical instrument, but as flying artillery. The front lines of a mechanized war are chaotic, obscured by smoke, electronic jamming, and rapidly shifting formations. The Soviet Air Force recognized that in this environment, loitering and designating targets through a high-resolution targeting pod was often a luxury their pilots would not have. They needed an aircraft that could live in the dirt with the motorized rifle divisions, operating from austere, unpaved forward strips just miles from the contact line. This required an engineering approach that prioritized extreme mechanical resilience over aerodynamic efficiency or electronic sophistication. If you enjoy detailed deep dives into military engineering and strategy, subscribe to the channel. I've got a lot more planned. The heart of this resilience is that titanium bathtub. The ABVT20 alloy was chosen because it offered the highest ballistic protection per millimeter, theoretically capable of stopping direct hits from 23mm anti-aircraft shells. The tub surrounds the pilot from the floorboards up to their shoulders. Even the canopy glass is aggressively armored, featuring a flat, heavy front windscreen designed to resist bird strikes at low altitudes and high speeds, as well as small arms fire from directly ahead. But this immense physical protection introduces the first major engineering compromise of the aircraft. Because the titanium tub is so massive and inflexible, it dictates the entire internal geometry of the forward fuselage. You cannot easily expand the cockpit or change its shape to accommodate upgraded avionics or larger multifunction displays. Consequently, the pilot is wedged tightly into a narrow, restrictive space. To say the ergonomics are poor by modern standards would be an understatement. It is a dense, chaotic scattering of analog dials, mechanical gauges, and toggle switches. When flying at 50 feet above the trees at 500 miles per hour, checking a vital engine instrument requires the pilot to look down into this dark metallic hole, taking their eyes off the terrain when they can least afford it. Furthermore, the tub creates severe visibility restrictions. The pilot is essentially sitting deep inside a trench. The side rails are high, and rearward visibility is virtually non-existent. To solve this, Soviet engineers mounted a periscope on top of the canopy. This small rearview mirror system allows the pilot to check their 6 o'clock, but it is a clumsy, narrow field of view solution to a problem created by the armor itself. The price for surviving a direct hit to the cockpit is an environment where the pilot struggles to see the threat coming in the first place. This theme of solving one problem only to create another extends directly into the propulsion system. The Su-25 is powered by two R95Sh non-afterburning turbojet engines, which were later upgraded to the R195 standard in newer models. These engines were chosen for one primary reason: they are incredibly robust. They lack the complex variable geometry of modern fighter engines and do not rely on fragile afterburner rings. They are designed to ingest a terrifying amount of battlefield debris, gun smoke, and dirt, and keep rotating. More importantly, for the Soviet doctrine of forward deployment, these engines are omnivorous. While they prefer standard aviation kerosene, they can run on diesel fuel or even low-octane automotive gasoline if the logistical supply chains break down. However, this rugged simplicity extracts a heavy toll on performance. Turbojets are notoriously thirsty, especially at the low altitudes where the Su-25 is mandated to operate. They lack the bypass air efficiency of modern turbofans. As a result, the Su-25 has a surprisingly short combat radius. When fully loaded with weapons and flying a low-altitude profile, its range is severely restricted, meaning it must be staged incredibly close to the front lines to be of any tactical use. Additionally, these engines run incredibly hot. At the low altitudes and relatively slow speeds of a ground attack run, they project a massive infrared signature, turning the tail of the aircraft into a brightly glowing beacon for heat-seeking missiles. This thermal vulnerability became painfully apparent during the Soviet war in Afghanistan in the 1980s. As the Mujahideen acquired advanced man-portable air defense systems, commonly known as manpads, the Su-25 fleet faced a crisis. Missiles like the American-made Stinger or the Soviet-made Strela would track the intense heat of the R-95 Shaich exhausts. When a missile detonated near the tail, the shrapnel would instantly shred the engine. Because the Su-25's engines are mounted tightly against the fuselage to reduce asymmetric thrust in the event of an engine loss, they sit very close to one another. Early in the Afghan conflict, engineers realized that a missile hit on the right engine would send high-velocity turbine blades and shrapnel directly through the thin aluminum fuselage, instantly destroying the left engine as well. The engineers in the Sukhoi Design Bureau had to act fast, implementing a brute force modification that perfectly illustrates their design philosophy. They installed a 5mm thick steel firewall vertically between the two engine bays. They didn't try to redesign the airframe to space the engines further apart. They simply welded a massive steel plate right down the middle. This firewall successfully stopped turbine blades and shrapnel from crossing over, ensuring that if one engine was obliterated, the other could still safely bring the aircraft home. But again, the laws of physics demand a toll. Adding a thick steel plate to the tail, combined with the Freon fire extinguishing systems and the sponge-like reticulated foam shoved into the fuel tanks to prevent explosive vapor ignition, added significant weight to the rear of the aircraft. To maintain the center of gravity, adjustments had to be made, and the overall payload capacity suffered. The aircraft became heavier, slower, and even less maneuverable. It could survive a missile hit, but it was now even less capable of dodging one. This brings us to the aerodynamics of the Frogfoot, which are entirely dictated by the necessity of lifting massive amounts of ordnance from terrible runways. The Su-25 features a thick, straight wing with only a slight sweep on the leading edge. It is equipped with leading-edge slats and massive, double-slotted trailing-edge flaps. This design generates incredible amounts of lift at low speeds, allowing a fully loaded aircraft weighing over 38,000 pounds to take off from a cratered, unpaved strip in under 4,000 feet. The landing gear is similarly over-engineered, featuring massive, low-pressure tires and mudguards specifically designed to prevent the front wheel from kicking gravel directly into the engine intakes. The aerodynamic penalty for this high-lift, rough-field capability is immense drag. The thick wing restricts the Su-25 to subsonic speeds. In a steep dive, it is redlined at barely Mach 0.79. In level flight with a full combat load, it lumbers along at speeds that make it an easy target for radar-guided anti-aircraft artillery. It cannot rely on speed to escape the target area. It must rely on surprise, terrain masking, and electronic countermeasures to survive the ingress, and raw physical armor to survive the egress. One of the most fascinating aerodynamic quirks of the Su-25 is found at the wingtips. The aircraft utilizes split air brakes housed in pods at the very ends of the wings. When deployed, these pods clamshell open, creating massive aerodynamic resistance at the furthest outboard points of the aircraft. This design choice was made to allow pilots to enter incredibly steep, almost vertical dive-bombing profiles without exceeding the airframe's maximum speed. By placing the drag at the wingtips rather than on the fuselage, it provides a highly stable platform during the dive, preventing the nose from wandering while the pilot tries to line up unguided bombs on a tiny ground target. However, because these air brakes are located at the wingtips, any asymmetrical deployment or battle damage to one pod creates a violent, unmanageable yaw. To counter the threat of battle damage severing the hydraulic or mechanical links to the flight controls, the Sukhoi engineers ran the control linkages for the left and right sides of the aircraft along opposite walls of the fuselage. If a burst of anti-aircraft fire shreds the right side of the aircraft, severing those cables, the left side remains operational, giving the pilot enough control authority to keep the nose pointed toward friendly lines. So, after seeing how it actually performed, do you think the design approach was worth it? Let me know in the comments. When you strip away the theoretical specifications and look at the dirt of real-world operations, the Su-25 presents a stark contrast to its closest Western counterpart, the American A-10 Thunderbolt II. Aviation enthusiasts frequently compare the two because they share a similar mission profile, but their underlying philosophies are drastically different. The A-10 was built as a loitering tank plinker. It was designed to fly over the Fulda Gap in Germany, loiter in the airspace, and use its massive GAU-8 Avenger 30mm rotary cannon to systematically dismantle Soviet armored columns. The A-10 is a sniper rifle built around a gun, optimized for long endurance and relatively precise fire. The Su-25, conversely, is a sawn-off shotgun. It is not designed to loiter. Its mission profile involves flying low, popping up over a ridgeline, dumping a massive barrage of unguided rockets onto a wide area, and immediately turning for home before the enemy's air defenses can lock on. While the Su-25 does have a powerful internal gun, the GS-H-32 30mm twin-barrel cannon, it is not the centerpiece of the aircraft in the same way the GAU-8 is for the Warthog. The GS-H-32 is a fascinating piece of brutalist engineering in its own right. It utilizes a GAST principle, where the recoil of one barrel firing operates the action of the second barrel. This allows for an exceptionally high rate of fire without the spool-up time required by electrically driven rotary cannons. But the recoil is so violent that it shakes the entire airframe, blurring the pilot's vision and vibrating the mechanical flight instruments to the point of unreadability. Because the gun is mounted on the underside of the fuselage, slightly offset to the left, firing it continuously induces a noticeable pitch down and yaw motion. Pilots are trained to fire in short, controlled bursts, utilizing it as a weapon of last resort or for strafing soft targets in passing, rather than as a precision anti-armor tool. Instead of relying on the gun, the Su-25's primary method of destruction comes from the 10 hardpoints under its wings. These pylons can carry up to 9,000 pounds of ordnance, but their typical loadout consists of massive rocket pods, such as the B-8M1 carrying 80mm S-8 rockets, or larger pods for the devastating 122mm S-13 rockets. The tactical doctrine dictates volume of fire over precision. The pilot approaches the target area at treetop level, pulls back on the stick to pitch the nose up, fires a ripple of dozens of rockets in a ballistic arc, and immediately breaks away, deploying a continuous stream of infrared flares from the massive countermeasures dispensers mounted on the tail. This pitch-up rocket attack, widely seen in modern conflicts in Eastern Europe, looks incredibly inaccurate from a Western perspective. And technically, it is. The dispersion of unguided rockets fired in an upward arc means they scatter over a wide area, functioning more like an airborne mortar barrage than a precision strike. But this tactic perfectly illustrates the operational reality of modern trench warfare. The airspace directly over the front lines is saturated with overlapping layers of radar-guided missiles and highly advanced manpads. Flying directly over a target in level flight to drop a gravity bomb is almost guaranteed to result in the loss of the airframe. The pitch-up tactic allows the Su-25 to deliver a suppressive shockwave of high explosives while keeping the aircraft itself out of the most lethal engagement zones, maximizing the chances of bringing the titanium tub and the pilot back to the dirt strip. The avionics on board the Su-25 reflect this blunt force approach. For decades, the aircraft operated without any form of modern head-up display or glass cockpit. The pilot relied on a simple ASP-17 mechanical reflector sight, projecting a glowing reticle onto a piece of angled glass. Target ranging was provided by the CLEN-PS laser system, mounted in the nose of the aircraft. The CLEN-PS perfectly demonstrates the nested loops of Soviet engineering compromises. It was an ingenious solution to provide accurate slant-range data to the weapon's computer without relying on bulky, heavy radar systems. The pilot would place the aiming reticle over the target, activate the laser, and the system would measure the distance, automatically calculating the impact point for the unguided bombs or rockets. However, there was a severe price to pay for this simplicity. The CLEN-PS lacked any form of video screen or targeting pod interface. The pilot could not zoom in or verify the target visually beyond what their naked eyes could see out of the thick armored glass. Furthermore, the laser system generated massive amounts of heat. It could only be operated continuously for about a minute before it had to be shut down to cool off. If a pilot missed their first pass, they could not simply circle around and try again. The targeting system would be locked out on thermal cooldown, forcing them to either drop unguided ordnance blindly or return to base. The defensive avionics were equally archaic and demanding of the pilot's attention. The primary radar warning receiver, the SPO-15 Berioza, did not feature a clear digital display showing the exact type and location of a threat. Instead, it used an array of glowing amber and green lights arranged around a central aircraft silhouette. When a radar system locked onto the Su-25, the pilot had to instantly interpret a complex, flashing pattern of lights, accompanied by a screeching audio tone to determine if the threat was ahead, behind, or to the side, and whether it was a short-range anti-aircraft gun or a long-range surface-to-air missile. In the high-stress environment of a low-altitude attack run, with the aircraft shaking and the ground rushing by at 500 miles per hour, deciphering these flashing lights required an immense amount of cognitive load. Efforts to modernize the Su-25 have met with the hard limitations of its original design architecture. The Su-25SM and later SAE-M3 upgrade programs attempted to drag the airframe into the 21st century by incorporating GLONASS satellite navigation, modernized HUDs, and improved electronic warfare suites. But the fundamental constraints remain. You cannot change the shape of the titanium bathtub. You cannot significantly alter the center of gravity without destroying the flight characteristics. The aircraft remains heavily reliant on unguided munitions because integrating modern, heavy, precision-guided standoff weapons requires larger data buses and sensor suites that the cramped airframe simply cannot accommodate. The modernization programs also highlighted the inherent friction between the original meat grinder doctrine and the realities of shrinking military budgets. The Su-25 was designed to be relatively expendable in the grand strategic vision of a massive conventional war. The assumption was that airframes would be heavily damaged or lost, and factories would simply stamp out replacements. But in the modern era, producing new combat aircraft is extraordinarily expensive, forcing air forces to keep these aging airframes flying decades past their intended service lives. Maintenance crews patch bullet holes with riveted sheet metal, swap out engines in muddy fields using rudimentary cranes, and send the aircraft back into the fray because there is simply nothing else in the inventory capable of absorbing that level of punishment. The legacy of the Su-25 is defined by its brutal adherence to its original design mandate. It is not an elegant machine, it does not look pretty on a static display line, and it does not boast the extreme technological integration of a fifth-generation fighter. But in the conflicts it was actually built for, from the mountain passes of Afghanistan to the grueling artillery-scarred trench lines of Eastern Europe, the Su-25 has validated the decisions made by the Sukhoi engineers decades ago. They understood that low-altitude close air support is not a clean surgical operation. It is an ugly, chaotic, and highly destructive environment where technology often fails, sensors are blinded, and survival comes down to how much raw metal you can put between the pilot and the enemy's ammunition. The Su-25 succeeds precisely because it makes no illusions about the nature of the war it fights. It accepts the immense physical and aerodynamic penalties of its armor, its engines, and its manual systems, trading operational efficiency for the sheer, stubborn ability to sustain catastrophic damage and keep flying. It is a flying testament to a doctrine that prioritizes the brute force of survival over the finesse of avoidance. If you like this deep dive, Leaving a like helps get it out to other military history fans. Thanks for being here.